problem where we are given 3 point masses at the edges of, they are at the corners of a right triangle, and the right triangle is shown along with the values of the masses and with the legs of the right triangle as well as the hypotenuse. And our task is to find the net gravitational force on each of these 3 point masses. So the first thing I'm going to do, and this will be useful, I'm going to first find the angle theta formed right here. So theta is easy to find. It's the inverse tangent of 3, the adjacent leg, over 4.5. Like that. And when I plug this into my calculator, I get theta equal to 33.7. So, theta then, and we'll use this again later, is 33.7 degrees. Okay. Whoops. And I'm going to erase. Now, before I start calculating any forces, I'm going to draw this picture again, and then I'm going to just draw into my new picture, my new drawing. It will contain only the, there we go, finally made it smaller. So I'm going to draw this again. Here we go. Here's one point, one of the point masses, here's another one, and here's the third. And here are the lines connecting the point masses. So there's the right triangle, M1, M2, and M3. And now I'm going to draw into this picture the different forces acting on each point mass. So mass 1 gets pulled down by mass 2. So this is the force of 2 on 1. And it also gets pulled diagonally along this line by 3. So that's the force of 3 on 1. Mass 2 gets pulled up. So this is the force of mass 1 pulling on mass 2. And mass 2 gets pulled to the right. So here I'm showing now the force of 3 on 2. Last one is M3. Mass 3 gets pulled up along that dotted line, the connecting line. So this is the force of mass 1 pulling on mass 3, mass 1 on mass 3. And lastly, mass 2 pulls mass 3 to the left there, like that. Okay, now, this may seem like many forces, but actually, we only have 3 different forces here. What we have is F12, which equals F21. The equation is the same for both. And here's that equation. It's big G. Let me move my theta over to here. This will be where I put it for now. And move this over. So again, the equation is big G times the product of the two masses, M2 and M1, over the radius, the distance between them squared. So I have M2 times M1 divided by the distance between them squared. So I'm going to use this equation over and over to find the 3 different forces. So that's the first force I'm going to find. Then I'm going to find the force between 2 and 3, which of course is the same as the force between 3 and 2. And that's big G times M3 times M2 over the square of the distance between mass 3 and mass 2, like that. And let me take this picture, and I'm going to copy this, move this guy over down to here, and just to make things a little easier, I'm going to make that smaller. Oops, if I can, my board is not agreeing with me today, so let me just come over. Okay, the last force I'll need to find is the force between mass 1 and mass 3, which of course is the same as the force between mass 3 and mass 1, and it's M3, M1, divided by the square of their separation distance. This is 1. The square of their separation distances, the denominator. So I'm going to take my calculator and plug in big G, okay, which is the same. It's always going to be 6.673 times 10 to the negative 11, and M1 is 25. M2 is 39, and their separation is 3 meters. Okay. And rather than let's see. No, I'll go ahead and calculate this out along with G. So I do G times 25 times 39 over 3 squared, and I get 7.229 times 10 to the negative 9 newtons. Oops. Like that. I'm going to do the same thing for the next force. Okay. M3, I can write, I can plug in for M3, the value is 56. M2 is equal to 39. And their separation, the distance between those two masses, is between 2 and 3 we have 4.5. Don't forget to square 4.5. So when I multiply all of this out, right, G again is 6.67 times 10 to the negative 11. So I plug that into the calculator. I have 56. I'm also multiplying by 39 and dividing by 4.5 squared. I calculate the second force here to be 7.197 times 10 to the negative 9 times 10 to the negative 9 newtons. And it's just a coincidence that these two happen to be close to each other. They won't always be close to each other. The last is F3, so I plug in M1 and M2, and the bottom is the R squared, the distance between them squared. So M1 I need, that's 25. I also need to plug in M3 in the numerator, which is 56. Right? The product of the masses, M1 and M3. And the denominator is the distance between them squared. And that's 5.41 squared. So I type this into my calculator. 25, 56, 5.41 squared, and I get 3.192. So I've erased the equation, and this is 3.192 times 10 to the negative 9 newtons. Alright, I found all of the forces in my diagram. But look at the diagram here. Okay? Look at this. Here, to find the net force on M1, I have to add two vectors that are not perpendicular. Right? The first is like this, and going tip to tail, the second's like that. So the second vector, to add these, I have to break the second vector into its components, and once I've done that, I can almost ignore the second vector, the original second vector. So let me move this back over. I can take this second vector away because I've represented it with components, and to find the resultant, the net, F net we might call it, I find the total x force and the total y force, so F y net, and the net x force, x net, and then I use the Pythagorean theorem. This squared plus this squared equals that squared. Okay? So that's what I'm doing next. Okay, so here I am. I'm back here to my original picture, and I've deleted the other stuff down here. Because I look at my diagram, and the first thing I notice is that this force, F21, and this force, F12, are both y forces. they're not at an angle, so I don't need to find their components. Likewise, F32 and F23 are x forces. They lie on the x-axis. So I don't need to find their components because they're already on the x-axis. The whole point of breaking a force into components is to represent it with only x's and only y's, only x forces and only y forces. So the only angled force for which I must find the components is F31. And of course, F31, it will have an x and a y component, which will be equal in magnitude to the x and y component of F13. Right? So what I'm going to do is I'm going to find the components of F13, draw them in here to the picture, and then they're going to be the same as the components for F31. And in fact, I'll take this down, and I'm going to remove the angled forces and represent those forces with just, here we are, with just components. So F13, it was up like this, right? Well, the x component then points like this, and the y component is up like that. And let me do a better job with the x. It's like this. And, whoops, and the y was up like that. So here is, in purple, the x component of that force, and here's the y. Similarly, this force, F31, was down at an angle, so it has a downward y component. And let me take this away. Let me make that a little bit more down looking. That's better. F, y, and it has an x component pointing over to the side. F, x. Good. Now I'm going to clean up my drawing because this is getting messy. Let me take away all of these. These are not necessary. And let me move M1 somewhere where I can actually see it. So here's M1 over here now. Good. I'm on my way there. So now I can look at my drawing. I have just x components, just y components, only x forces and only y forces. The first thing to do is find these components, fx and fy. Okay? So let's do that next. So I know this angle, right? I found that early on. It's 33.7, still there. Which means it's a simple matter finding fx and fy. Fx is the hypotenuse, right, F13, times the cosine of the angle. And Fy is that hypotenuse, F13, times the sine of the angle. So in place of F13, I'm going to use this here and also in this equation. Theta, I know to be 33.7. So I'm going to calculate this out. Oops. Oh gosh. I'm going to calculate this out on my calculator. And first I'll do fx, then I'll come down and do fy. Right? So here we go. Let me erase this. Okay. Fx is 3.192 times 10 to the negative 9 times the cosine of 33.7. So when I plug that in my calculator, what I get for fx, I get that fx is equal to 2.656 newtons. 2.656 newtons. Of course, though, we have times 10 to the negative 9, like that. Now, Fy, we said, was the hypotenuse, which is 3.192 times 10 to the negative 9 times the sine of 33.7, like so. So I can go back into my calculator, and I can say times the sine of 33.7 now. And what I get for Fy 1.771 times 10 to the negative 9. 1.771. And by now, I'm really getting annoyed of writing times 10 to the negative 9. So I'm going to replace all of those times 10 to the negative 9s, right? I'm going to erase this, this, and I'm going to replace them all with a little n, which means nano. Nanonewtons, 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 and likewise here, nano. Nano means times 10 to the negative 9, just a lowercase n, okay? And, okay, get that clear? We are now ready to finally find the total gravitational force, the net gravitational force, on each of these three masses, right? So, I've got my givens here. I'm going to make those a little smaller. There I am. I've got a little bit more working space. And the first thing I'll do is I'll find the final answer for M1. So the net force squared equals the net x force squared. I don't like this notation because I don't like writing out really long subscripts. Like this here is a super long subscript. So what I can do instead is, instead of saying the net, I can say the sum of the forces, like that. That big squiggly sign is the summation sign, sigma. And it means take the sum of, or the total, or the net. Really just think of it as net force. The sum of the forces, F, equals the sum of the x forces squared plus the sum of all the y forces on M1. So on M1, on mass 1, what are the x forces? And let's add them up in parentheses right here. Well, I look at my picture, and I see that the only x force on M1 is this, the x component of F13, right there. So in the parentheses, all I need is just that one x component, 2.656 nanonewtons. And I'm going to take out units for now because I'm going to run out of space otherwise. For the y's, what do I have in the y direction? Well, I have two y forces. I've got this, Fy, which was the y component of F31. And then I've also got F21, which is this. So inside of the y parentheses, I need to add together those two forces that with arrows next to them, right? This one and this one. So let's add those together in the parentheses and get all this way. So what I add then for Fy is 1.771 nanonewtons plus the other y force, which was 7.229. And you might be thinking, shouldn't those y forces be negative because they're down? Well, you can make them negative. You can choose for down to be the negative direction. But what you see is it doesn't matter, because when we square it, right, any negative sign will go away, right? So when I calculate out the total force, the net force, I do 2.656 squared plus 1.771 plus 7.229, and that's all in parentheses, and I square that. And I take the square root, and I get, well, the net force squared was 88 about, and when I square root that, I get the net force equal to about 9 now we can round for sig figs, so we'll say 9.4 nanonewtons. Or if we really wanted, we could go back to times 10 to the negative 9. And now I'm done for mass 1. Let's do the same thing for mass 2. It's the same equation. So I can leave that up. Mass 2 is this one here. So, that's going to be really easy. For the x forces, all I have is F32. That's the only force in the x direction. So F32 is this. And right here then, I do 7.197. For the y forces, all I have is F12. And that's this one here. No other y forces. Whoops. So for the sum of the y's, all I need is F32, which is 7. Wait, let's see here. What am I doing? I need F12, which is 7.229. That's how many nanonewtons. So I plug this into my calculator. I add the two squareds, and I get 104. And then I square root it, and I get about 10.2. So the sum of the forces is 10, we'll just call it 10 point, for sig figs, nanonewtons. Or 10 point times 10 to the negative 9 newtons. And I could really say 1.0 times 10 to the negative 8 if I wanted. Right? Good. Done with M2. Now let's do M3. So I can leave the equation, same equation. No need to write it again. And M3, here we go, last one. The sum of the forces squared, the net force, right? The net force is the net x force squared plus the net y force squared. So, what are all the x forces I have to add up here? What are the x forces I add that I sum? I'm going to add up F23 and Fx. So here's F23, there's Fx. It'll be 7.197 plus, 7 point, lost it, 7.197 plus 2.656. That's the total x force. Fx, here it is, plus F23, here it is. Now I need to add the total y force and square it. The total y force is just Fy, 1.771. So I look at my calculator, I type in, open parentheses, 7.197 plus 2.656, close parentheses, squared, plus 1.771 squared, and then I square root that, and I get 10 as well. Look at that. So the total force on mass 3, the net force, on mass 3 is about 10 nanonewtons as well, or 1.0 times 10 to the negative 8, if we care to write it that way. So those are our final answers. And that's how you solve a problem like this.